Why? So that the speed of propagation of gravitational effect according to Newton is infinity, that is, it's instantaneous. So if mass m moves, gravitational field at a distance point changes instantly. But this this entire argument, this analysis, this finding faced a problem. Problem because of a strange observation. And you know this, the beautiful interface of mathematics and physics. For this two subjects are absolutely married to each other. So now see the role of observation. We saw that what mathematics taught us. It told us that there is something which is propagating with infinite speed. Now, a strange observation was the following. Suppose there are two particles A and B, they are traveling to each other with velocity v1 and v2. Let me reiterate that what I am trying to tell you, that at the end of this you will exactly know what is gravitational wave and why we are so excited about it. That is the most important point to do research on a field. Unless you feel excited about it, you can't do it. So suppose there are two objects moving to each other with velocity v1 and v2 and there is an observer sitting here. Okay. So this means this observer is seeing that this particle is traveling a distance v1 in unit time and this particle is traveling a distance v2 in unit time. That is the meaning of the word. Right? So velocity v1, v2 with respect to this observer. Now suppose I ask you the question, what is the velocity of B as perceived by A? Now that we know the relative velocity, that in unit time A travels a distance v1 and B travels a distance v2, therefore the distance between them is reduced by v1 plus v2. And therefore A will think that B is coming towards him with velocity v1 plus v2. That happens when you sit on a train and another train comes from the opposite direction. Okay. So this is what we have learned in your school, that it is v1 plus v2. This is the prediction of Newton's law of motion. Okay. So the relative velocity between two objects are v1 plus v2, and our daily experience when sitting in train exactly satisfies this, and we were very happy till an observation. Observation is the following, that suppose this object starts traveling with speed of light. Then the speed of that object as perceived by A should have been, according to this law, v2 is c, then v1 plus c. So the speed of that object should have been v1 plus c from the perspective of the other observer. But it turns out, if we travel speed of light, the relative velocity should be v1 plus c, but it turns out it is same as c. The speed of light doesn't change. Now this is very, very paradoxical observation, because this took the entire world by surprise. Because he is traveling a distance c in unit time, he has traveled a distance v1 in unit time, so in unit time the distance has been reduced by v1 plus c, as simple as that. So how is it possible that he is seeing still its velocity c as static observer seeing, he is also seeing c v1 to c. So people got absolutely perplexed, and there we needed a genius like Einstein, who pointed out that this can be explained by only one way. When you are saying that this is traveling a distance v1 in unit time and this is traveling a distance c in unit time, then what is the distance traveled by B as observed by A in unit time? You are assuming the unit time of this observer and unit time of this observer are same. How do you know this? If the time flows differently. If the time of this observer and time of this A are different, then it is possible that since the definition of speed you have distance by time, if the time interval changes, the denominator changes, it is possible that the sum will still be c. So it's a very simple mathematical calculation to try to find how the time of this observer and time of this A are related. So Einstein first pointed out, in fact the special theory of relativity is nothing but this, that the meaning of time are not universal, they are different from different observers. So Einstein said that when you have two frames, one is traveling with velocity v with respect to the other, suppose this is one origin, this is another origin, and they were together at t equal to 0. After time t, this has traveled the distance c. So take any point here. If you say this point from this origin is x prime, and this point same coordinate is from here is x, then clearly x is nothing but x prime plus v into t, because it has traveled the distance v into t from here to here. So x is vt plus x prime. So that equation you know, and there is no displacement along the other direction. So he wrote x prime is x minus vt, y prime is y, z prime is z, and wrote a very important quantity t prime is t. So this is what Galileo and Newton thought. The time in both the frames are identical. So time interval t prime is same as the other. So one frame is unprimed and other frame is primed. Now if you differentiate both sides dx prime dt, but dt is same as dt prime. So dx prime dt prime is the velocity in one frame, dx dt is the velocity of a particle in another frame, and this v being a constant, it may minus v. So this is the relative velocity formula that we derived earlier, that we talked about earlier. And according to this, speed of light should change. If it's c in one frame, it will be c minus v or c plus v in the other frame. And if you now differentiate again, then this v drops out because this is a constant. So acceleration in both the frame are same, which tells you that all inertial frames are equivalent. So this is the meaning of Newton's law of gravitation. But here the problem is, the inertial frames are same, but speed of light is constant, it doesn't change. That is the crucial observation which puts question about Galilean transformation between two frames moving with respect to each other with uniform velocity. And Einstein said that time cannot be universal. There is no universal clock. Just as you have your own position in space, you have your own time. So position is relative. If you are closer to somebody, farther from somebody, flow of time is also relative. So he said that change that relation to this. I am sorry that this is a little bit invisible. It is instead of x minus vt, it is x minus vt by root 1 minus v square by c square, and v is the velocity of between the two frames, and these are the new relation. Now you can see that when your velocity is much less than speed of light, the relative velocity between the two frames, then you can neglect the v square by c square quantity with respect to 1, and you can get back x prime is x minus vt and d prime equal to t, which Newton thought. But the moment your velocity becomes very large and close to c, then you cannot neglect. And if you now calculate the velocity in two frames, dx prime dt prime is the velocity and dx dt in the other, you will see that the relative velocity formula will tell you speed of light remains constant. So you can think of the following, that it's a kind of very clever back calculation. So the speed of light remains constant. And this is the result which is known as Lorentz transformation. But this result, try to understand, has a very important implication. It tells you that if you travel with speed greater than speed of light, then it's a disaster because you land up to an imaginary quantity. And you cannot, your positions may be related by a equation, t prime may not be equal to t, that is fine, but t prime cannot become imaginary. Then the physics loses its meaning. So then Einstein said that, okay, but as you can see, nothing can move faster than speed of light, and therefore this question does not arise. So people ask me why nothing can move faster than speed of light, because if you just employ force, it will accelerate and exceed the speed of light. He said no, it cannot, because as I say, if you now calculate the relative velocity between two moving objects, then it is always less than equal to c. And we find that nothing can move faster than light. Why? Because he said the mass changes with velocity. And now if the mass changes with velocity, when that frame, the observer attains the speed of light, any mass in that frame attains any mass which has a velocity v with respect to an observer has a mass equal to infinity, because v becoming c, it becomes infinity. Now velocity equal to c implies mass infinity, and acceleration is forced by mass, acceleration becomes 0. So moment you reach the speed of light, you cannot accelerate anymore and your speed cannot increase. So everything is happening, no problem. Nothing can move faster than light. Even if you apply force, it will not accelerate because its mass has become infinite when it has reached the speed of light. So c is the maximum possible speed. And since mass started changing with velocity, How does it change? Because we are doing work on the object, because you are employing force, and till date you knew that when you do work, the force is the work done is converted into kinetic energy. But now Einstein taught us it not only gets converted into kinetic energy, of course it does, but also it changes the mass. So energy is converted into mass. Which energy? The work done by you. The energy you consume from petrol is getting converted into the mass when the car is moving. So the energy is converted into mass, and therefore the reverse is also possible because of the reversibility. And Einstein found there is a beautiful relation equal to mc squared. From these equations you do a little bit of algebra. This is pretty simple. But it tells us from a small mass, since C is large, we can produce a huge energy, which you know the consequence. And also from a huge energy, you divide by c squared, you can create small masses. And that is exactly what you do when you say that a particle is created in the accelerator. So when Higgs boson was created, how it was created? Because a huge energy was converted into mass by the colliding protons. So these equations are crucial. This equation, it tells you mass can be converted into energy and energy can be converted into mass. But then, what is why we are stating all this? We are stating all this because this is observed thing. And what happens to Newtonian gravity? Newtonian, this says that nothing can move faster than light in vacuum. This is what Einstein taught us now, till right now. And Newton said gravitational effect propagates instantaneously with infinite speed. So there is a clear clash. Einstein said no, it's not possible. Nothing can, no gravitational form of energy cannot propagate. Because energy is equivalent to a mass. So how can propagate with infinite speed? It violates relativity. So this contradicts Einstein's special relativity, which you have learned, I told you right now. So in vacuum, no information can travel its speed faster than light. This is Einstein's relativity. And Newton saying that gravitational effect is propagating with infinite speed. So something is wrong. Clearly something is wrong. And that wrong was addressed by Einstein again, by an evolutionary concept. He said that this Newtonian concept of gravity is not correct. So he said that Einstein rejected this concept of force, gravitational force. And this probably you have certainly, I will be quick on this because I know that yesterday you had lectures on this subject, but I will give you the essential idea that I need to explain gravitational wave. So what Einstein did, Einstein came out with a beautiful idea. He said that why two objects will attract each other when they are at a distance? This product of two masses. He said this Newtonian description is incorrect. He came out with a beautiful idea. He said, consider a flat space where you know that the sum of the three angles of a triangle is 180 degree, the shortest distance is a straight line, and the circumference of a circle is 2 pi r, and etc. etc. But you know that this breaks down the moment you take a curved surface. On the surface of convex surface, the sum of the three angles of a triangle is greater than 180. This is a flat surface where equal to 180. So this is what is called Euclidean flat surface. This is a curved surface. This is a concave surface which is less than 180. So Einstein said that Newton tells a body travels along a short straight line in absence of force and accelerates when there is force. This is what Newton tells you. I hope you agree because Newton's first law tells you everybody continues to be in a state of rest or of uniform motion in a straight line in absence of force. But if you apply force, there will be acceleration. That is Newton's law. Einstein said that, see, when Newton says this, he essentially says that if you take any surface, take any 2 points, what is the shortest distance? Straight line. So Newton tells you that in a flat surface, any object without any force travels along the shortest path. And it can accelerate when there is force. Now, when I have written in board acceleration means curved line, you can ask me one important question. You can tell me that why do I think so? Because I show you that there is acceleration, but it is not curved. I am releasing it from my hand. It is going in a straight line. Okay? It is going in a straight line. It is not curved line, but it is accelerating. Correct? But why I am saying that acceleration, or Newton and Einstein saying acceleration means curved line? Because remember, acceleration means it is straight line visually in our three-dimensional space. But consider the equation, it satisfies x equal to ut plus half dt squared. If I ask you to plot in xt plane, will it be a straight line? So remember, whenever there is an acceleration, this term power of t will be more than 1. And then the path will be a curved line, right? And whenever power of t is 1, then the path will be a straight line when there is no acceleration. So for this reason, Einstein said that everything travels in space-time plane in a curved path whenever there is a force, because force leads to acceleration, what Newton thought. So this is Newton's idea. So Newton told you that if you consider xt plane, then everything will travel in a curved path whenever there is force, that is acceleration, and whenever there is no force, then it will travel in a straight line in xt plane, x equal to. Einstein said, so Newton said no force, straight line, in presence of force, curved line, in space-time, not in space. In space it is traveling in a straight line, but in space-time. Einstein said, take the space-time, and don't think that this is traveling in a curved surface, but instead assume that space-time is itself curved. If the space-time gets itself curved, then the shortest distance, there is no force. So it is following Newton's first law, shortest distance. The shortest distance is the curved line. And if the because you have to stay within this plane. If the shortest distance is a curved line, seeing that it's a curved line, you are thinking that there is a force. There is no force. So Einstein said that what Earth has done, Sun has done, Sun is not attracting Earth. Sun has changed the space-time around it. And since it has changed the space-time, the Earth, the shortest path is now an ellipse. So this is a remarkable idea that Einstein said that there is no force, everything is traveling along the shortest path, but the shortest path is changing because the space-time is getting curved. And why it is getting curved? Because of the presence of mass and energy. So a mass and energy doesn't attract another mass, it changes the geometry. So this is what is general relativity, in short. So Einstein says that the space-time is curved, and presence of mass energy curves the space-time. The shortest distance is now a curved line giving an illusion of acceleration, and due to the existence of a gravitational force. So this illusion of force originates from curved geometry. Very good. So there is nothing called gravitational force. It's a manifestation of geometry. It's a very, it's extremely revolutionary statement after Newton's achievement of explaining everything. So suppose you have a theory which is explaining almost everything, suddenly you say this is wrong. People will not accept. So people didn't accept initially. But he said, okay, let me be a little more mathematical. He said, fine. Consider in a flat Euclidean-like geometry the distance between 2 points x, y, z are x plus d, x, y plus dy, z plus dz. There exists a coordinate which is called Cartesian coordinate, where you can write the distance as this, which is Pythagoras theorem, which tells you that there exists a coordinate called Cartesian coordinate, where the distance is the square of the differentials and the coefficients are 1, 1, 1. It is not true in all coordinates, but there exists one such coordinate. But the definition of curved spaces, curved geometries, there is no coordinate where you can write this as 1, 1, 1 coefficient, but it will always be 1 plus some modification, one function, which are functions of x, y, z. So this is the definition of curved geometry, that in curved geometry there cannot be any coordinate system where you can write as 1 dx square, 1 dy square and 1 dz square. And this F1, F2, F3 captures the curvature, and they are called the metric of the space. So with this mathematical understanding, you remember that you learned that time is now also like a coordinate. You have just learned that everybody has its own time. Time is not universal, same for everybody. So in that case, in four-dimensional space-time geometry, because I am thinking about space and time, in four-dimensional space-time, the curve geometry should look like 1 plus f1 d square, 1 plus f2 dy square, 1 plus f3 dz square. It should be plus 1 floor f4. Forget about c square, because c is this, in order to make the unit identical, this is distance and this time. So I multiplied by a pure constant, universal constant. So this makes the unit same. So forget about this. Minus 1 plus 4 dt square. It should have been plus, I think. Why suddenly this minus is appeared? This is a bit tricky, because in 4D, three-dimensional space and one time, the natural generalization should have been all same. But why this minus? This minus is because of the simple fact that unlike x, y, z, time has a crucial difference. Though just as you have your own space, you have your own space, you have your own time, you have your own time, then normally in our usual speed they are almost equal, as Newton thought. But for high speed they are not equal. But the difference is, in x, y, z you can travel in both the directions. You can come here and you can go back, right? But can you go back in time? You cannot. So this is guaranteed by this minus sign. If I have time, I will explain at the end. This minus sign ensures that. So time, though it has a very similar footing as coordinates, space coordinate, but not exactly same. There is one difference. It is not in your control that you go back in time. So this is what is the four-dimensional distance in space and time, and we are dealing with space-time curvature. Remember, not space-time curvature. Why? Because we are curved, we are generating. So we are assuming what Einstein said. So assume that space-time is curved. Yeah?
One question.
Yeah.
You are telling that time is not propagate in inverse direction.
Yeah.
So if the spatial coordinate have the same property, then you are doing all with minus dx square minus dy square.
But then this will become plus, because essentially, okay, if you're just asking, I mean, I thought I could explain at the end. The reason is the following. You can put a overall minus sign, that's a matter of convention. You can multiply both sides by minus, so it becomes minus, but then it becomes plus.
No, my question is not that.
Yeah.
My question is that since time does not propagate in the reverse way, so you are giving a minus sign.
I am giving not a minus sign, I am giving a sign which is opposite to space. That's the whole idea.
But if x, y, z coordinate has the same property that of t, then you
also... So it doesn't, then it will be same, but it doesn't. That's the reason, x, y, z, you can have both directions. Proper.
That is
but
why you are taking.
That is the
but if you have the
No, you can do the other way around. You can say that all x, y, z are similar. You can travel both. It is not the minus or plus important. Important is the difference between them. There has to be a difference between these two. If you take this as plus, all this as plus, and this as minus, then I'll show you that only thing there is, I am assuming one important thing, that nothing is traveling faster than light. Okay. If you travel faster than light, then you can move reverse direction of time. You can create time machine. You know all these funny stories. But I need to draw a light cone and I will explain you. I will do that. Okay.
No, my question is not that.
The question is what?
If x, y, z have the same property that of t,
then all will be plus. Then all will be plus.
I am telling you.
That is correct. That is absolutely correct. In fact, in some people, just to make it look like that, they put one imaginary IT here.
Yes.
And call IT to be some tau, then it becomes plus, because I square is minus 1. Okay? But then it is called that I have converted this 1, 1, 1, minus 1, which is Minkowskian character, into a Euclidean character by changing the concept of time. And that is exactly today, in fact, I asked your organizer that whether I will talk about this. This is exactly what Stephen Hawking did in order to explain the black hole geometry and black hole. So, but today I cannot have, don't have time to say that. Okay. These coefficients which measure curvature can, okay. Now these coefficients are functions of x, y, z, all these coefficients. Okay. So this we measure the curvature can depend on time and space both, and this something, this coefficient leading to fluctuation, propagation of the space curvature like a wave. So what do we mean by this? What do I mean? I mean by this is the following. Can I get a sheet of paper please from anybody? So suppose you have this, and then because of some mass somewhere here you have produced a curvature. Okay, curvature. Now in this curvature, which is characterized by those functions, are function of x, y, z, t. How they can be function of x, y, z? Suppose this mass has produced the curve, some curve here, this curve. Okay. Now if this mass starts moving, when the distance from the mass from here changes, and the curvature that this mass produces at a point, at a distance point, depend on its distance. So if the mass moves away, this curvature will change, and then mass comes back again, the curvature will again change. So what will happen? It will start moving like this, and see, this is looking like a wave. The wave of what? Change of curvatures because of the motion of the